Hello and welcome to Little Big Physics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we discovered that we can quantify the heaviness of different materials and predict how heavy an object of a given size and material will be. What we learned then will prove useful for what we'll try to do today. You might recall a few episodes back where we tried to predict how objects would fall, but there was something that we were missing. For some reason, some objects fell faster than Sackboy, while others fell more slowly. Today, we'll investigate what makes different objects fall differently. Our job starts out pretty simple. Let's just gather a bunch of blocks with slight differences and see if they all fall at the same speed. If they do, then that particular difference doesn't affect how they fall. If they don't, we found something that does affect how they fall, and we can investigate further from there. First, just to provide extra confirmation to our belief that some objects fall differently than others, let's put together a total potpourri of different shapes, sizes, and materials and see what happens. Out of everything in our little collection, there was at least some variation in falling speed, but admittedly not much. Let's get more specific now that we've seen a difference. What if all of these were the same material? Now, different blocks still fall at different speeds, but not the same speeds they fell before. The material apparently does have an effect, or at least some property that changes with material, like heaviness or density. Size and/or shape evidently makes a difference too. Alright, let's get a bit more scientific and narrow down the variables further. What about blocks of different thicknesses? Our job here is complicated by the fact that changing one property changes a few others, like how changing the material changes the density and thus the heaviness, or changing the thickness also changes the heaviness. Let's give it a try. We can see pretty clearly that the thicker blocks fall more quickly. Thus, thickness and/or weight, since thickness affects weight, affects how quickly a block falls. Does the orientation of a block affect how it falls? Let's take a really thin block and have it fall both upright and sideways. Does it make any difference? Apparently not. Is anything different if one of the blocks is rotating and the other isn't? It might seem that way at first, but the rotating block is actually inconsistent about whether it falls faster or slower, and the degree to which it lags behind or pulls ahead actually doesn't increase over time after the first moment or so. It seems more like spinning the block before dropping it gave it some initial speed up or down, depending on how it was rotating at the moment of its release. What about material? We've already confirmed that changing the material has an effect, at least indirectly, since it could just be that changing the material changes the weight, and the weight is a deciding factor, but let's see if we can find a pattern in which materials fall faster. I've gathered a bunch of blocks that are identical in every way except their material. What happens? I threw Sackboy in this time too, just for fun. There's a very big difference, but it's an interesting one. Recall the densities we found last episode. Some materials actually have the same density. It just so happens that those materials also fell side by side in this trial. Take another look. Stone and metal, which are tied for the heaviest material, fall together. Then there's glass, rubber, and wood, along with Sackboy, though Sackboy curiously only weighs a bit under 1/3 as much as those other blocks, since they weigh 3.33 smasses and he weighs 1 smass. It's possible that Sackboy is a special case though, so I'll look at him again later, if not today. Then there's sponge, which has a unique density. Then, after dissolve, which I guess has another weird density value, there are cardboard and polystyrene, tied for the lightest material. Thus, it seems that material doesn't directly affect how an object falls, but rather that material's density and/or weight has an impact. Let's try varying the size next. 3 blocks, all the same thickness and material, but different sizes. What happens? The bigger blocks fall more quickly. How big of a difference can this make though? Let's get ridiculous now and make the biggest, heaviest block we can within the confines of a Little Big Planet level. It'll be hard to get much useful visual data out of it, but we can graph it like we did the falling blocks in the gravity episode. A quick run with the old apparatus is pretty straightforward. Now let's do the opposite. The lightest block we can manage. I went with a minuscule block of polystyrene, the lightest material along with cardboard, in the thin layer. Run the trial, and it definitely falls a bit more slowly. A lot more slowly. Incredibly slowly. Finally, it arrives, drifting slowly downward like a snowflake, or something like that. Aside from just being entertaining, this sends us a few clear signs. For one, significant differences in weight can make significant differences in how things fall. Second though, let's recalibrate the graph and run this again. Does something look a bit different from the other times we've graphed falling blocks? The graph this time, instead of a curve, is a straight line. Let's extrapolate a little. Suppose we graph the height of an object as it fell. From what we've seen, the heavier an object is, the more drastic the curve, although we're yet to determine if there is an upper limit on how steep the curve can be. The lighter an object is, the more linear the curve, approaching a completely straight line as the heaviness gets closer to zero. Keep in mind though, that whatever kind of curve this is, these are both the same kind of curve, and the object starts from a standstill at the very top, so the tip of the curve is always flat. The simplest model I can think of that fits both of these graphs is a curve that starts out horizontal, then curves and turns into a straight line. For this to be true, then for the heavier blocks, it must be that they just don't reach the part where the line becomes straight before they reach the ground. For the lighter blocks, the curved part must be so short that it immediately becomes straight. Does anything like this exist though? It turns out that in the infinite, and sometimes infinitesimal, expanses of mathematics, the answer to such a question is almost always yes. And it is here too. The most basic equation that I could come up with to describe this is the following. It might look weird that there are literally no numbers here, so I'll walk through what each part of this means. The h is how high the object is at any given moment, meaning that this equation just tells us how high up it is in the air. The t that you see in two places on the right side of the equal sign is how much time has passed since the block began falling. If we graph h and t, it should look just like those graphs we made in the acceleration episode. E is just a number actually, it's kind of like pi. It's just a symbol that we use to refer to a very specific constant number. All the other letters, A, B, C, and D, can be just about anything at all, and they might be different for different objects, but they'll always be the same for the same object. For example, for our small piece of polystyrene, A might be 2, or might be something bigger or smaller for our giant metal behemoth. This is a lot easier to take in if you look at what happens as each number changes. Here, I've graphed the equation where I can tweak each number individually. The solid red line is the equation we're creating. The dotted blue line is the line that the red line eventually becomes after enough time passes. As a changes, the initial height, h, when t is 0 changes, as does the arc of the curve before it turns into a line. B changes, making the curve turn into a line more or less quickly. As c changes, the steepness of the line changes. Finally, as d changes, the entire graph just moves up or down. How do we make this look like the graphs we're trying to model then? For every scenario, the graph should start out as a curve and then turn into a downward slanted line. This means b should be negative, since if b is positive, the graph will start out as a line and turn into a curve instead, which is the opposite of what we want. If b is negative, then the graph turns into a line like we want. Since c determines the slant of the line, c should also be negative so that the line goes downwards. A also shouldn't be 0 since the equation will just be a line otherwise. Now I can get more specific to each scenario. For something like the giant metal block that takes a long time for its graph to turn into a line, b is probably pretty small, since b is what determines how big the curved part is, and a needs to be such that the curve is completely horizontal when t is 0, since the block wasn't moving at first. C is probably a pretty big negative number, since that means it'll fall more quickly, which is what we saw happen. It probably looks something like this. For the small piece of polystyrene, b is probably a really big negative number, since its graph turned into a line pretty much immediately. A has to be small then, for the curve to be horizontal when t is 0. Finally, c is probably smaller, since the polystyrene fell more slowly. D can be pretty much anything in either case, since that just depends on how high the block was when it started falling. Let's see if we can get this model to fit the data that we collected a few episodes ago for a falling block. My usual tools, mostly Microsoft Excel, actually aren't capable of fitting this kind of equation to a set of data, so I had to break out Mathematica, a much fancier program made by the same company that runs Wolfram Alpha. The dots on this graph are the data that we collected for a falling block a few episodes ago, and the solid line is the fit generated by Mathematica. I feel obligated to point out that equations don't usually fit the data this well, but I guess we took a step in the right direction. Now, keep in mind that this doesn't mean we've necessarily figured out exactly how to model a falling object, but it works for this particular set of data, and it should certainly work for the big block of metal and little scrap of polystyrene too, since we designed it specifically for that. Is there a way that we can figure out how to calculate A, B, C, and D then? Well, theoretically, probably, if we make a lot of these graphs to see how each term changes when we tweak the weight and initial speed of the block, but I have a feeling that we'll make things a lot easier for ourselves if we give ourselves a better foundation first. For one, we don't actually know the mechanics yet behind blocks falling the way that they do. All we know is that there is something making the block's acceleration decrease the faster it goes. We might call that a type of resistance, and since it happens to blocks moving through the air, let's call it air resistance. Regardless, I think we should come back to this part once we've done a little bit more exploration of what makes objects move the way that they do, instead of just how they move. It's been a pretty long day already anyways. Our work might not be done just yet, but there's no doubt that we're making progress on understanding how objects move in Little Big Planet. I think that this is a nice example of how the world can sometimes be deceptively complex, where something as simple as a falling object requires so much investigation and such a detailed model. I have plans to come back to this though, so rest assured that we'll get to the bottom of this someday once we know more than we do now. In any case, until next time, and stay curious.